Welcome to
لا تنسوا
Aerodynamics,
الإعجاب
a
بالفيديو
field that
والاشتراك
has
في القناة.
existed for thousands of years, since humans started designing wind-driven sailboats and chased the aspect of flight. This course will serve as an introduction to all things aerodynamics, covering the basic fluid dynamics principles, modern modeling techniques, and application. The word aerodynamics comes from a combination of the Greek prefix aero, meaning air, and dynamics, which is the study of motion due to forcing. Put simply, this is the study of how air moves around objects and forces them. From a theoretical mechanics perspective, aerodynamics is a subset of fluid dynamics, which is the study of how all fluids move due to forcing. From an engineering perspective, aerodynamics serves as the foundation of aerospace engineering, both aeronautics and astronautics, which is a field that specializes in the development of aircraft and spacecraft. People that specialize in aerospace engineering are usually familiar with aerospace materials, flight mechanics, aeroelasticity, and propulsion, among other things. For those of you familiar with fluid mechanics, your first question might be, why just air? Doesn't what we learn in fluids apply here? Of course it does. The theory behind fluid mechanics does not change when we specifically focus on air, but there are reasons for the distinction. Due to the composition of the planet, throughout history humans have learned to traverse through two major fluids. Air is the dominant gas, and the study of air is aerodynamics. Water is the dominant liquid, and the study of how water moves is hydrodynamics. The fundamental equations are the same. There is no difference in the conservation of momentum for water and air. However, water comes with the added benefit of being assumed incompressible, meaning the density is constant everywhere in the field, and that significantly simplifies the math. Air, however, is often compressible, especially in high-speed flight, and this can make the math more difficult and causes us to need more equations, like the conservation of energy in the equation of state, to find all the variables. Second, water is quite heavy compared to air. This means that in order to be held up in the water, it is easier to use the buoyancy force. But in order to stay up in air, we need to generate a vertical force, which is known as lift. Think of it this way. A neutrally buoyant fish really needs to only worry about using its fins to move forward. A bird, however, needs to worry about generating lift to stay up while simultaneously generating force to move forward. So, these unique aspects of moving through air and the usefulness of air transportation are the reason we have specific courses dedicated to it. And once you've learned aerodynamics, there is a ton you can do with it. Obviously, aerodynamics experts are needed in the design of aircraft. Commercial aircraft, uncrewed area vehicles, fighter jets, all foundationally operate on aerodynamic principles. Automobiles heavily rely upon lowering air resistance to decrease fuel consumption or improve race time. Rockets and ballistics often reach hypersonic speeds and rely on aerodynamics to know where they are going and to get there accurately. Aerodynamic forces show up in countless sports, including the cycling to lower air drag, or golf and baseball to manipulate the flight dynamics of the ball. Some people use aerodynamics to save the planet by designing technologies to harvest wind energy. And lastly, in order to get to the vacuum of space, you have to travel through the atmosphere, which can be tough with such high altitudes and low air density. So, knowing and specializing in aerodynamics opens up a wide variety of interesting career opportunities. Now that I've hopefully convinced you we should want to study aerodynamics, how do we do it? Specifically, let's consider how studying aerodynamics is different than how we would approach fluid mechanics. Let's consider an object in an airflow, in this case an airfoil. First, aerodynamicists are generally concerned with the global body forces that the flow causes. Consider the way a fluid mechanician would study this type of flow. They would be very concerned with defining the exact flow field as it develops over the object. In general, they would seek a mathematical definition of the entire flow. An aerodynamicist would approach things a bit differently. Their primary concerns are the body forces produced, things like the overall lift and drag, the moments produced, specifically if body forces are generated from away from the center of gravity, and the pressure distributions that produce these body forces and moments. In order to get to these body forces, you do need to know something about the flow itself, but you can do more estimating and modeling to predict these forces. As a result, aerodynamics is much less exact than how we approach fluid mechanics. In fluid mechanics, the conservation equations are solved exactly or approximately given a very simple geometry, like a channel, a pipe, or a flat plate boundary layer. In aerodynamics, we generally can't arrive at exact solutions. The geometries are much more complex. There are a wide variety of airfoils of arbitrary shape, spheres with three-dimensional separation, and a wide array of ground vehicles that can change the flow behavior. So, we do a lot more looking things up in documented tables that have empirical values. For example, let's say we have a plane flying at some velocity and angle of attack that we know. How could we know what lift it's generating and making sure it can stay in flight? In this case, there's way too much going on to solve the flow field everywhere. So what we do is we mark down the meaningful parameters, like flow speed, angle of attack, and what type of airfoils we're dealing with. Then, I take out a reference that has pages of tables where people have documented what forces they found when they put an object like this in the flow. You then find the table with the parameters that matter for you, like the airfoil type and flow speed, and you look up the approximate lift you would expect to see at that angle of attack. With some work, you can then apply this to the entire plane and ensure that your lift is sufficient to maintain flight. While we care about the body forces generated by the flow, we're also interested in the entire force balance of a vehicle, much like a free body diagram. When an object like a plane moves through the air, it experiences a number of forces in various spots. Generally, our goal is to move steadily, meaning no acceleration or deceleration in any direction. In order to maintain steady flight, we need to counter the forces from the air. Consider a wing attached to a plane. As the plane moves through the air, it experiences lift, which is perpendicular to the flow velocity. In order not to fall out of the sky, the lift must equal the vehicle weight. Similarly, the air force along the flow direction is the drag force. To counter the drag, we need thrust. Often the thrust is produced by a turbine, a propeller, or burning propellant. If the drag and thrust are not equal, we either speed up or we slow down in the flow direction. Additionally, the central location where the body forces act on the foil can change depending on the flow conditions. This causes issues, because then the lifting force produces a moment about the plane's center of gravity, inducing rotation. If we want to maintain steady flight and not do backflips, we need to create a force that counters this moment, which can often be done at the tail of the aircraft. The tail has a different airfoil with different lift force. So, you can see how aerodynamicists need to know a bit about the fluid mechanics, but they also need to keep the forces on the entire vehicle in the back of their mind as they do their analysis. And finally, in aerodynamics, we end up needing to solve for more flow variables. The velocity field and the pressure field are the main players in introductory fluid mechanics courses. In order to solve for the velocity and pressure, the two unknowns, you need two equations which end up being conservation of mass and momentum. For the majority of fluid mechanics, until you explore compressible flow, that's about it. However, in aerodynamics we often need a few more flow variables, especially in high speed or high altitude flight. First, the density in air can vary a lot more easily than it can with other fluids. So, that means we have an additional variable to solve for, and need another equation. This equation is generally the conservation of energy. Unfortunately, when we introduce this new equation, we get more unknown variables. Specifically, we add in the unknown of internal energy and temperature. Two more unknowns means needing two more equations, and that leads us to the equation of state and the perfect gas equation. In the end, we have 5 unknowns and 5 equations, and solving for all of the unknowns becomes a bit more difficult. Outside of the equations, it's important to note that from an engineering perspective, knowing the temperature in a lot of aerodynamic vehicles is absolutely critical. Re-entry vehicles get super hot. So hot, in fact, that we have to design specific lightweight materials that don't disintegrate. So, knowing the max temperatures we can expect tells us how to design the vehicle, and better predictions lead to more efficient and cost-effective designs. To summarize, in aerodynamics we take a slightly different perspective than we did in fluid mechanics. We focus a bit more on the body forces generated by the fluid, and oftentimes these bodies have complex geometry. Then, once we know about the aerodynamic forces, we need to think of the vehicle as a whole and consider a force balance to maintain steady flight. We use previous observations to tell us about the forces we can expect because, more often than not, we can't solve for the flow field entirely. And we often have to work with more variables than we did in fluid mechanics, and more equations to solve for those variables. So that wraps up the first lecture. I hope you enjoyed it, and now we can put our aerodynamicist hats on and move forward. I'll see you next time.